Hello and welcome to NASA headquarters in Washington, D.C. I'm Steve Cole from the Office of Communications. We're here today to tell you about the upcoming launch of NASA's fifth Earth Science mission in less than a year. The Soil Moisture Active Passive Mission, or SMAP, is set to launch from California 3 weeks from today. SMAP is going to provide the most accurate, high-resolution global measurements of soil moisture made from space ever. Today we have 4 panelists to tell you about the mission. Let me introduce them to you. First will be Christine Bonniksen, SMAP Program Executive in the Science Mission Directorate, Earth Science Division here at NASA headquarters. Kent Kellogg, SMAP Project Manager from NASA's Jet Propulsion Laboratory in Pasadena, California. Dara Entakabi, SMAP Science Team Lead from the Massachusetts Institute of Technology in Cambridge, Massachusetts. And our fourth speaker is Brad Dorn, SMAP Applications Lead from the Science Mission Directorate's Applied Sciences Program at NASA headquarters. After our panelists give their presentations, we'll take questions from media here in the audience, on the phone lines, and for those watching online at nasa.gov. If you have a question during that time and are watching online, please use the Twitter hashtag AskNASA. If you're a media on the phone lines, when you have a question, please dial *1 and you'll be put in the queue for questions. Okay, well then we'll get started with our first panelist, Chris.
Thank you, Steve. Good afternoon. The Soil Moisture Active Passive Program, or SMAP, will be launching from Vandenberg on the 29th of January, and it will focus on the water that lives and moves through the soil. This information will improve our knowledge of weather, climate over land, as well as water-related hazards. If you could put up the first slide, please. SMAP will be joining our 18 operational missions that study the Earth's systems. These issues that are addressed by this are climate change, things like sea level, and freshwater resources. Our on-orbit satellites, along with the air and ground observations, monitor the Earth's vital signs. The timing of this launch is really fortuitous, since this is the UN's National Year of Soil, and it was kicked off on the 5th of December. Organizations in countries around the world have volunteered to participate in the SMAP program. Countries that are involved are those like in Kenya, Australia, Argentina, and Canada. And they are voluntarily supporting our data collection, algorithm verification, and understanding of the massive amounts of data that will be coming from this mission. With the launch of this project, decision makers will better be able to understand the water cycle and how soil moisture fits into that. The soil actually gathers the precipitation prior to it entering the rivers and then evaporating back into the atmosphere. As a result, soil moisture impacts many areas of human interest, including flood, drought, disease control, and weather. If you could run the video, please. This is a first look at the amazing satellite that we've built. It has 2 instruments on it. The active from our name is a radar, and we have the passive instrument, which is a radiometer. The radar will be providing our high-resolution data, and the radiometer provides the high-accuracy data. When you put these together, it's very similar to looking through both lenses on a pair of bifocals at the same time. As a result, we will have a highly accurate global map of soil moisture for our scientists to use. This dual instrument was key to the National Academies of Science Earth Science 2007 Decadal Survey ranking of this as a high Tier 1 mission. And NASA is very excited with the fact that we are able to launch this within 10 years of receiving that recommendation. The global soil moisture freeze-thaw map will be available to scientists every 2 to 3 years. And after the CATS launch, the Cloud Aerosol Transportation System that is being launched this coming Saturday, we will be focusing in on the SMAP launch and the knowledge that we will be getting from its data. If you could put up the next slide. The SMAP launch, as Steve said, completes an 11-month period that started with the launch of the Global Precipitation Measurement System in February in Japan, and NASA is looking forward to the synergistic measurements that we are going to be getting and the scientific advancements that will result with all these new instruments that we will have launched. I will now turn the floor over to our SMAP project manager, Kent Kellogg.
Thank you, Chris, and good afternoon. SMAP is jointly developed by NASA's Jet Propulsion Laboratory in Pasadena, California, and the Goddard Space Flight Center in Greenbelt, Maryland. JPL is the lead center, has project management and system engineering responsibility, developed the spacecraft, developed the overall instrument and the large spinning antenna subsystem that you see on SMAP, as well as the radar instrument. Goddard provided the radiometer instrument, and both centers participate in science data processing. So if we could roll the launch sequence video. SMAP will launch into a polar sun-synchronous orbit, a 685-kilometer altitude, 6 a.m. equator crossing time on January 29th from Vandenberg, the Space Launch Complex 2 facility. We will 5 minutes after liftoff, we will separate from the first stage, transition to the second stage, and deploy the fairing. We have a fairly long unpowered coast period, followed by a brief second burn of the second stage, which will deposit us very close to our final science orbit. The Delta II should leave us in a attitude that's optimized for communication with TDRS and for having our solar arrays pointed at the sun. We should, as soon as we separate onboard sequences, we'll release the solar array, stabilize the spacecraft, and initiate communication with the ground through TDRS. We should achieve a power positive condition on the observatory as early as 8 minutes after separation, or it could take as long as 50 minutes depending on the configuration and orientation of the spacecraft after separation. We'll spend our first 2 weeks in space checking out all the spacecraft systems, and at that point we will begin the deployment sequence for the large reflector boom antenna. So if we could roll that deployment animation. The reflector boom assembly deploys in 2 steps. Starting 16 days after launch, we will deploy the boom. That process takes about 16 minutes. Once that's done, we will spend several days confirming that we've had a successful deployment and making sure that the spacecraft attitude is behaving as we expect with this new configuration. Now you'll notice that the spacecraft looks somewhat like the tail wagging the dog with this very large antenna deployed with a very small spacecraft. So we want to make sure that the spacecraft is behaving with this new mass distribution. 20 days after launch, we will unfurl the large antenna. It starts at 12 inches in diameter. It's initially bloomed. This is passive release of the strain energy. That'll bloom the antenna out to about 7 feet in diameter. And then we will do the powered deployment, which will deploy the antenna out to its final 20-foot in diameter size. That process takes about 30 minutes to complete from start to finish. And following that, again, we'll spend several days making sure that the reflector is properly deployed and that the spacecraft attitude is behaving as we expect. Once we have the antenna deployed, we will check out the instruments. We will do our final adjustments to the science orbit, and then 50 days after launch, we will begin the process of spinning this antenna up. So if we could run the spin-up animation. We initially want to spin up to just about 4.5 RPM. This is a low rate spin rate. You'll notice as we begin to spin up that the spacecraft actually counter-rotates in the opposite direction. This is by design and is a feature of the fact that we're trying to spin up a very large structure with a relatively small spacecraft. Once the antenna has reached a stable spin rate, the spacecraft attitude system will regain sun pointing very quickly, and we continue on. We will stay at about 4.5 RPM for a couple days, again making sure that the spacecraft attitude is behaving as we expect, and then we'll gradually increase the spin rate up to the full science spin rate of 14.6 RPM. All that should be completed by 60 days after launch. Then we'll go through the full instrument checkout. We'll have both the radiometer and the radar sharing the antenna aperture at the same time. The beam is pointed about 40 degrees off to the side of the spacecraft so that as we spin the antenna, a spot on the ground rotates under the spacecraft, mapping out a swath that's 1,000 kilometers wide. This allows the SMAP observatory to map the entire Earth in 2 to 3 days based on latitude. So it's a very efficient mapping system. The commissioning time frame will be completed about 90 days after launch, at which time we'll begin the science calibration and validation process. Now we've spent a lot of time doing a lot of testing on the system, starting at the component level, the assembly level, the subsystem, and then eventually the system level. If we can roll the build-up and test sequence, the spacecraft was assembled a year ago last fall, the fall of 2013. This shows the solar array in one of its deployment tests. The video that you're seeing now is the radar system. The radar mounts on one of the spacecraft panels. It's not part of the spinning complement, and you see it being installed on the anti-sun panel. This is the radiometer in a spin test that was completed right before we installed the radiometer and feed onto the spacecraft last January, a year ago. The last piece of the instrument that came together with the observatory is the large reflector antenna. You see it in one of its many deployment tests that we did. It was installed on the observatory for the first time in January as well, so that completed the observatory assembly. We've done a lot of testing over the last year, including electromagnetic compatibility testing that you see here. That's very important for an L-band microwave instrument. We did dynamic testing, which simulates the launch vehicle environments. We did thermal vacuum testing, which simulates the temperature and vacuum conditions in space. All of our system level testing went extraordinarily well. We had no major issues. We completed our last mission scenario testing over the summer and early fall. You see a spin test here that we did over the summer. The observatory was shipped to Vandenberg on October 15th. It's now completed all the planned observatory level activities that we had planned for Vandenberg. The observatory is fueled, and we began integrated operations with the United Launch Alliance in preparation for mating to the rocket this week, and we'll actually mate to the rocket early next week. So with all the testing and work that's gone on behind this, we have a lot of confidence that this mission will meet both its technical and scientific objectives and will enjoy a long and productive life in space. And with that, I'd like to turn it over to our science team leader, Professor Dara Entakabi of the Massachusetts Institute of Technology.
Thanks, Ken. Good afternoon. The SMAP observatory carries two science packages, a microwave radiometer and a microwave radar. These two science instruments packages and the mission operations concepts are specifically optimized to provide high-quality soil moisture data. The radiometer instrument acts much like a camera. It sees the ambient light environment, in this case beyond the visible range in the microwave range. And the specific advantage of the microwave range is that you can see in daylight and at night. You can, unlike a conventional camera, see through clouds. You can penetrate moderate vegetation and, in fact, peer into the soil for a few inches to actually measure the volume of water in the soil. That's the basis for using the radiometer to make the soil moisture measurements that SMAP does. Now, the resolution, the size of the features on the ground that you can see with the radiometer is limited by the size of the antenna, the reflector in this case, and that's about 40 kilometers for the SMAP radiometer and antenna. In order to augment that, SMAP carries another instrument package, which is the radar, and that one acts like a flash camera. It actually emits light, or in this case, a microwave pulse, and looks at the reflection of that off the surface. And much like the flash camera, you can see a lot more detailed features on the surface, but you're susceptible to scattering of the surface vegetation and surface roughness. So it's less sensitive than the radiometer to soil moisture, but it's at much higher resolution, in fact, on the order of 3 kilometers. The combination of these two is what produces the SMAP high-quality soil moisture retrievals. The mission operations concept is demonstrated in the video, if you would run that, please. The observatory orbits the Earth pole to pole at about 680 kilometers, and it rotates about itself as it's orbiting the Earth in order to cover a wide swath. That is necessary in order to revisit the same spot on Earth every 2 to 3 days, depending on latitude. Here you see the radar making measurements, highest resolution at the edges, and here's the radiometer making its measurements throughout the swath using the same shared antenna. And here is the soil moisture retrieval based upon the combined radar radiometer measurements. This strip is the result of one orbit around the Earth. Here you see 2 orbits, adjacent orbits that are about 3 hours apart. And after 2 to 3 days, the jigsaw puzzle gets filled and you get a global map of surface soil moisture. Now, what's unique about SMAP science returns is that it has returns in 2 very distinct areas. Next slide, please. One of them is in fundamental understanding of how the environment works. So it's addressing some fundamental earth science questions. The second is in the arena of applications. SMAP also provides data that affect our everyday lives in terms of dealing with some really serious natural hazards. In terms of earth science, the 3 fundamental cycles that make life possible on Earth, the water cycle, the energy cycle, and the carbon cycle, over land are linked through the soil moisture variable. If it wasn't for the soil moisture variable, these 3 processes over land would vary independently, but they don't. They work in concert like gears in a clock. They are linked together through the soil moisture variable. Now, if we're making projections of weather on a short-term basis, numerical weather predictions 0 to 10 days, or if we're making longer-term projections of climate, for instance, water availability under a changing climate, variability in climate, and global warming, the regional temperature response and the regional water availability response are a function of how we link these 3 cycles together. As water evaporates from soil water to vapor in the atmosphere, it feeds the water cycle. It takes energy to vaporize water, and water vaporizing cools the surface and maintains the temperature, much like humans have evolved through sweating to maintain and regulate the body temperature. The same thing happens for the Earth system. And as plants transpire and pick up biomass through absorbing carbon dioxide from the atmosphere and releasing water vapor, they're engaged in the water and energy cycles as well. So these 3 cycles are intimately linked through the water variable, and through measurements that SMAP can make, we can test and improve models that we use for atmospheric weather prediction and climate change projections. Now, in terms of applications, next slide, the there are some natural hazards which actually very much relate to surface soil moisture, and soil moisture measurements made by SMAP will directly feed into those. I have here an example of a map put out by the National Weather Service. This is updated every day. It's produced at the 13 or so river forecast centers. And basically, this is a map, county by county, over the United States, of the deficit in surface soil moisture. That's the capacity of the soil to hold water minus the actual soil moisture. It's in units of inches. And what this map is used for is that river forecast centers produce this and then transmit it to about 122 weather forecast offices. These are located around the country. And what forecasters at weather forecast offices do is to look at this map, the soil moisture deficit, they look at the precipitation map that's incident at the moment, and where they see precipitation exceeding the flash flood guidance or soil moisture deficit, they issue a flood warning or a flood warning immediately. Now, this map of surface soil moisture cannot be generated from probes that are in the ground to measure soil moisture. They're just far too far and few in between to be able to produce such a map at county level. So what the operation does is that they take precipitation history measurements, history of precipitation. They use models to make an estimate of what they think the soil moisture ought to be. Now, SMAP will make direct measurements of this variable at much higher resolution, at about 10-kilometer resolution rather than county level. Another example of SMAP applications is at the other extreme, and the next slide. This is the US drought monitor. Again, this is an operational product that's, in this case, updated weekly. This is an estimate of the agricultural drought that's existing in the United States right now. And you can see the big dry in California is very prominent in this latest graphic. Now, the very definition of agricultural drought is a deficit in soil moisture. And again, in this case, there's nowhere near adequate ground stations to be able to produce such a map. So this map is also produced with models that are fed the history of precipitation in order to produce an estimate of surface soil moisture. And again, SMAP will produce direct measurements of this quantity at high resolution, which will help refine and prepare these two important applications for the next generation. And with that, I'll turn it over to Brad.
Thanks, Tara. Hello, everyone. The Applied Research Program of SMAP targets opportunities for SMAP data sets to directly impact decision makers in the United States and around the world. Next slide, please. They do this by providing access to simulated data, as you see here in this slide, to applied users and applied researchers so they can evaluate this data in their decision-making processes and discover what it can be used for and how it's going to impact those processes. The goals of the SMAP Applied Research Program are to engage users early in the mission development process, to improve the delivery of the data products, and to incorporate that community feedback into the mission process. Now, how do we meet those goals? One way is to engage the community called the early adopters. Next slide, please. SMAP mission has 38 early adopters. Now, these early adopters have been accessing data, simulated data that the SMAP mission provides. Now, these early adopters come from the private sector, they come from universities, they come from government agencies and non-government agencies. One of these early adopters is the United States Department of Agriculture Foreign Agricultural Service. Next slide, please. USDA is responsible for assessing global crop production on a monthly basis. And soil moisture is a major factor in crop production, if not the major factor in crop production. So as you can see here, the model with the simulated satellite data compared to the model data with just ground data. So you can see the completeness, the spatial resolution on the right side is much more significant than without the simulated data. Now, we have many early adopters that are focused on our own water resource challenges in this nation. One of those was mentioned earlier. It's the United States Drought Monitor, and it's run out of the National Drought Mitigation Center at the University of Nebraska-Lincoln. Roll video.
Soil moisture is really a critical component into understanding drought and where it's developing, how severe it is. Traditionally, soil moisture information has been acquired through ground-based measurements or probes in the soil, which are few and far between. So we're interested in SMAP to give us more detailed information on soil moisture variations across large areas and really fill in the gaps between where these sensors are on the ground to give us a more detailed spatial view of how things are changing in the soil over time.
As we get these data at a higher resolution, covering the entire country, we're going to do our jobs better. When you see the drought monitor map coming out each week, we're going to have more confidence in some of the inputs that we're looking at, especially with regards to soil moisture, are going to be of a higher level and of a greater quality and more utility than anything we've had up to this point.
The SMAP mission is a true innovator, not only in its groundbreaking space technology and its critical basic research, but also in its ability to integrate applied users early in the mission development process to accelerate the use of NASA data in decision-making processes. Back to you, Steve.
Okay, thank you, Brad, and thank you to all our panelists. All right, we'll take questions now from both the media and those watching online. Just as a reminder, if you are watching us online and would like to ask a question, please use the hashtag AskNASA. For the media on the phone lines, as a reminder, if you want to ask a question, press *1. We'll start with questions here in the audience before going to the phone line. First question, please identify yourself, sir.
Sure. Thanks, Steve. Eric Hand with Science Magazine. I guess first question's for Kent. I'm really impressed by this design. I mean, it looks like something out of a Dr. Seuss book, almost, you know, with this crazy boom and this really large reflector. Maybe you can tell us a little bit more about why this particular design was chosen, and also, you know, if it has any forerunners, if this was, you know, completely created here just for this mission, or if it's based on any older technology, older missions, and then finally, you know, what the most challenging part of this design is. What's the riskiest part of all these moving parts and weird torques and crazy unfolding booms? Thanks.
Okay, thank you. Yeah, let's see, there were several parts to the question. First of all, why this design? When you have two instruments sharing a common aperture, a reflector is a very efficient and cost-effective way to allow those two instruments to share that aperture. If we had to use something like an active array, we'd basically have to have multiple sets of array electronics to support each instrument function. Here we can have those electronics integrated comfortably in boxes where they could be more efficiently packaged, and the reflector supports both functions very, very efficiently. The spinning approach, as we mentioned, that's been used before for other science missions like QuickScat and Seawinds, for example. They used a spinning antenna very much similar to this, much smaller size, to again map the entire oceans in that case very efficiently. These large reflector antennas have been commonly used for communication satellites typically. In fact, actually much larger antennas have been flown. We are a smaller variant of a design produced by Northrop Grumman, so we've scaled down. We've done a lot of testing on this, particularly over the last year, to make sure that we have high confidence that it will work as intended during the deployment process. Does that answer the question? Okay.
Okay, we'll go to the phone lines with our first question from Sandon Totten, Southern California Public Radio. Go ahead, Sandon.
Hi, thanks a lot for explaining all this. I have two questions, one that should be relatively straightforward and another maybe a little more complicated. The first, do we know what percentage of the Earth's water is in soil moisture across the globe, like what kind of numbers it represents in terms of the overall water? And second, I was wondering, we're here in California, we're struggling with this drought. I was wondering if you could go into a little more detail about how this data could actually be used, not just to give us a picture of the drought, but to maybe help us deal with it or predict future droughts.
Okay, I'll take that. The fraction of water that's in soil is actually tiny. It's much less than 1%. About 97% of the water in the globe is locked up in the oceans, and the rest of that is in the cryosphere, in the ice. But that small percentage that's in the soil is rather important and very active because it's what's interacting with the terrestrial biosphere, with the vegetation. It's what's determining how much runoff occurs due to incident precipitation, how much fresh water there is in the rivers and lakes. And so it's a tiny amount, but a very important amount. It's not the percentage of the total that's important, but where that soil moisture is and what is affecting. The second question, does that address your first question?
Oh, yeah, totally. Thank you.
Okay. The second question is about the California drought. The measurements that SMAP makes will be direct measurements of the indicator of agricultural drought, which is the deficit in soil moisture. So it will produce a high resolution, at about 10-kilometer resolution, map of the drought. But droughts are initiated, forced, and maintained, but much larger scale processes. Things such as the interaction between the oceans and the atmosphere and over land and over continental regions, land and the atmosphere. So it's not just mapping the local California region, but seeing how the continents as a whole reinforce and feedback onto the climate system in order to make these things last beyond just weather scale.
Okay, our next question from the phone lines is Roseanne Skirble, Voice of America.
Yeah, thank you very much for doing this. My question is how SMAP fits into the complement of Earth monitoring instruments that were launched over the last year, and what it can do that we haven't been able to do before.
All right, I'll take the first part of that. One of the things that NASA is trying to do is to make sure that we have ways of measuring the various parts of the different cycles, the energy cycle, the water cycle, the carbon cycle. And so SMAP fits into that with going through the soil moisture, which we here at NASA have not been collecting recently. But I will turn it over to Dara to answer the rest of that question.
I think next couple of years is going to be very exciting for Earth science because of GPM, SMAP, and OCO2. These are three missions that are measuring key variables in the water and carbon cycle that's forcing the global system. So OCO2 will produce carbon dioxide columnar column dioxide measurements, as well as fluorescence. It will measure how much photosynthesis is going on in plants. That, with SMAP, is a very powerful measurement. You can decipher how the terrestrial biosphere vegetation is responding to soil moisture variations. With GPM, precipitation and soil moisture, the connections are obvious. One of them is the principal flux in the water cycle. The other one, soil moisture, is the principal state variable in the terrestrial water cycle. So the two together is really powerful.
Okay, one more question we have on the phone line, Frank Mooring at Aviation Week. Go ahead, Frank.
Thank you. I'm interested to know how, sort of the follow-up on that last question, and that's how the data from the SMAP instruments would be used to calibrate or refine or improve the data from other orbiting instruments. And I'm particularly interested in the GRACE satellites, which I understand measure the ground or the reservoirs of water in drought conditions. And this is an unrelated question, but I'll go ahead and ask it. And that's for Kent Kellogg, how the reflector, the single aperture, the reflector handles an active and a passive signal at the same time. Are they different frequencies, or how does that work? Thank you.
Should I go with the first one? Yeah. So, GRACE is a fantastic mission. It measures gravity anomalies. It's a non-photonic remote sensing mission. It produces estimates of density variations, much of it due to the columnar water that exists everywhere from the atmosphere, the precipitable water, all the way to surface soil moisture and into the groundwater. So it's a measurement of the total integrated water that it sees, but it's at fairly coarse resolutions, hundreds of kilometers. There's significant activities going on right now, combining surface soil moisture measurements, which respond on weather timescales and on very small spatial scales, and GRACE measurements, which are columnar and much coarser resolution. And together with models, these two very different resolution and very different sensing depth measurements can get integrated in order to produce a much better picture of the terrestrial water cycle. So this is an ongoing and well-recognized activity.
Okay, and the second question was how do the radar and radiometer coexist operationally on the same mission? It's a great question because you have this very noisy, active radar sharing the same aperture with a very sensitive scientific receiver that wants to live in a very quiet neighborhood. So it's a little bit like having a rock band sitting next door to a library. And the way we deal with that is the two measurements are at different frequencies, first of all, so that helps. The radiometer actually listens in between the radar pulses. So remember, the radar is an active instrument. It's sending out pulses, very short pulses, and then it's listening for a relatively long period of time. And the radiometer can use that long period of time to acquire its measurement. And then we have another layer of insulation, if you will. We have a great deal of filtering built into the system to make sure that the radiometer is protected from any noise that's being generated by the radar. And of course, in ground testing, we spend a lot of time evaluating those two instruments working together and making sure that the radiometer is not perturbed by the radar operation. So that's a very good question. By the way, we're not the first mission to fly a radiometer and a radar together. Aquarius did that as well. So there is some heritage and legacy there that we've benefited from and then built on that. So did that answer your question?
Thank you.
Okay. Well, we'll take a couple of questions at this point from social media. Over to you, Jason.
Hello. Our first question here comes from Twitter user William, who asks, curious, why 50 days before the antenna is spun up or 20 days before the antenna is deployed? Just an abundance of caution?
No, it's actually a very good question. We lay out very carefully the sequence of events that we want to do after launch. We want to deploy the antenna as soon as possible after launch, but we can't do that until we get all the engineering subsystems sufficiently checked out so that we know the attitude control is working, we know that the communication system is working, we have a cadence established with the ground system. There has to be a certain infrastructure working and operational with the spacecraft before we can deploy the antenna. The spinning operation, there's a little more flexibility there. We decided we wanted to do our final orbit adjustments before we spun up the antenna, but we need to get the antenna spun up in order for us to complete the final steps of the observatory calibration. We do have margin days built in, so there is a little bit of conservatism in the schedule. We don't want to rush. We want to be very careful and deliberate and make sure we have a chance to look at the data before we go on to the next step of the commissioning activity. But there is a very logical, thought-out sequence, and there's not that much margin embedded in it. But great question.
All right, next question is actually a couple of them combined from about data here. Carl on Twitter asks, what time frame will SMAP data become available publicly? Also, will this be available via FTP or data catalog? Also, Mike on Ustream's asking, once the data is made available to the public, will we get updates every day?
The science data acquisition begins 3 months after launch, after all the commissioning has been completed. The data will undergo evaluation. The data that comes down has to be calibrated and validated. That's intense activity at the beginning. The first release of the geophysical products takes place at 6 months after the start of the data acquisition. That's called the beta release. The instrument data, the radar and radiometer measurements, will get released 3 months after acquisition. This is just to make sure that all the calibration offsets have been implemented. And then the validated data gets released after 1 year. So that's the data that has been through the validation process. The early adopters enter agreement with the project, and they get access to the data alongside the science team because they are critical in the calibration and validation as well. And that gets them a chance to prepare to use the data operationally. So the data gets released basically on that schedule.
Wonderful. Last question here from Twitter user named Katie. Could the data from SMAP theoretically help us predict and possibly even mitigate or negate the effects of drought in the future?
The mitigation of droughts happens by knowledge of where it's happening, how it's expanding, and the prospects of it going away. Obviously, we can't affect the drought itself. That's a natural phenomena. But how we react to it and how vulnerable our systems are, our food systems, our water supply systems, how vulnerable we are is going to get affected by what information we have in order to deal with it on a timely fashion.
Okay, our next question is from the phone lines, Irene Klotz at Reuters. Go ahead, Irene.
Thanks very much. I just was wondering if someone had a spacecraft cost and mission costs. Thanks.
The overall commitment for NASA was that we would produce, launch, and operate this mission for 3 years for $916 million.
Okay, our next...
Including launch, yes, sir.
All right, our next question from the phone lines is Becky Oskin from Live Science. Go ahead, Becky.
Hi, can somebody address why it's important to measure whether the soil moisture is frozen or liquid and how that relates to, for example, flooding hazards or other hazards that the mission will contribute to?
Like that. The frozen thawed classification is one of the products that the SMAP mission will produce. It's mostly based upon the high resolution radar. There is a very strong signal change when the soil and the landscape freezes and when it's thawed. The principal reason that we're interested in that is the carbon cycle, but flooding is obviously also affected by frozen and thawed surfaces. The vast boreal forests in Alaska, northern Canada, and vast regions of Siberia, there's a lot of biomass there. And in the net, this biomass picks up carbon dioxide from the air and assimilates it into its leaves and trunk and branches, biomass. And in the winter, it slowly releases that. Over long term, in the net exchange is zero. It takes up as much as it releases. But depending on the duration of the freeze to thaw cycle in a year, that same location may be a net so-called source of carbon or a net sink of carbon. And as the boreal latitudes have a changing winter duration, some of these forests may change from a neutrality to being a net source or a sink. That is a very important component of the global carbon budget, and in fact, it's referred to as the missing carbon problem because we can't account for it. So SMAP and the carbon cycle, the SMAP measurements are entering the carbon budget calculations in that way.
Okay, we have another question from the phone lines. Roseanne Skirble again from Voice of America.
Yeah, I just wanted to, if you could address the challenges of turning this immense amount of data into practical products, things that can be used, that decision makers can turn to. Could you discuss that a little bit?
I'll discuss one aspect, but maybe I'll turn one of it over to you guys too, because the amount of data and the processing of it is complex, and most users couldn't just take raw data, agriculture users, and turn it into a soil moisture product that they could use. But we are producing higher level products, and you see that in some of these simulated products that they can use. And one thing about soil moisture is, and the reason we have so many anxious early adopters is they do know soil moisture is important, and they do know they need better soil moisture, because most of it's just modeled data from precipitation from a sparse set of ground stations. So adding this level of direct measurements is going to make a big impact in that, and you saw that in the video of the U.S. Drought Monitor. But they do need help, and that's where the mission comes in, and that's why we're interacting with these early adopters and producing products that they can use and that they can access. I don't know if you guys want to comment on the processing at all.
I don't know, in all these years, I've never had trouble explaining to someone why they need soil moisture. Soil moisture for atmospheric modelers is a state variable in their models. It's actually, they have to keep track of these variables, and every time they run a numerical weather prediction, they have to initialize the soil moisture. So they know exactly why they're making these measurements and how they're going to use it. In terms of crop models, in terms of terrestrial ecology models, they all have soil moisture as a state variable. It is the state variable of the terrestrial system, so it's not very difficult to explain. And surely farmers and drought monitoring, again, agricultural drought is defined as departures from normal in soil for soil moisture. So I don't think there's much difficulty in translating this into practice, science, or applications.
Okay, we'll go back to social media with a few more questions. Jason?
Wonderful. This question comes from Twitter user Derek, who asks, how long will NASA SMAP be able to remain in orbit?
Okay, I'll take that. Our requirement, the requirement that NASA imposed on the mission is for a 3-year science, 3 years of science operation. This is after the commissioning period, so it's a total of 39 months. However, we expect if the observatory is operating well during that period, that it will operate for many, many years beyond that. There's certainly no constraint on the life of the observatory from consumables like onboard propellant or anything like that. So we expect that we'll get many years of life out of the observatory.
Wonderful. Next question comes from Twitter user Justin, who asks, what is the mission cost of SMAP?
As I mentioned earlier, the agency committed to Congress that we would procure, operate for 3 years, and launch the mission for $916 million.
Wonderful. This last question comes from Twitter user Katie, who asks, will information from this mission help with analyzing compositional data from other planets to see if they have water?
The simple answer is no, we're looking down.
Okay, fair enough. I think that's all the questions we have for today. There's a lot more information about SMAP online that you can go and access all the way up to launch, and that's at the website www.nasa.gov/SMAP. And if you'd like to keep in touch with all the different earth science activities, the different missions that have gone up this last year, there's a website for that too, and that is www.nasa.gov/EarthRightNow. And of course, as always, you can follow along on all this activity on the many NASA social media channels. Just as a reminder, SMAP is scheduled to launch 3 weeks from today, January 29th, from Vandenberg Air Force Base in California. Thank you all for watching. Bye-bye.